Okay, good afternoon. Today we'll do a problem on, we'll try and do a real life problem. We'll try and design some traffic light system. A very simple one, right? Very simple one. At least you get the idea. Then you can move on and do some larger system, all right? Okay, we started this last week, but we got stuck because I think we were too ambitious. And we can't solve something as ambitious as that in a 45 minute time period. So what we started off with was, we had some basic traffic lights. You have your red, you have your orange, and you have your green, right? Okay, red, orange, and green. Okay, so this was your red, orange, and green. Now, what happens is that when you have your red light, you for quite some time, you hold it at red. So let's say a period of 60 seconds, right? You hold it at red. Then after that timer is up, remember, you have an input into your system to change the state, right? So after that timer is up, your input changes to 1. And once you have a 1, your light becomes green. Then it is held at green for a while, right? It is held at green for a while. Let's say another 60 seconds or maybe 120 seconds, right? It is held at green. Then what do you have? Then you have the third one, which is the last one, which is orange, right? Orange is in the middle. It's just an interim light, and that will stay at orange for 10 seconds. Now, how do we measure this? Now, the way to approach it is two ways. Let us say, one thing we could do is, if you look at the ratio, we said 60 seconds, 10 seconds. That is same as saying, one option is, if we have a clock pulse of 1 second, our clock pulse is 1 second or 1 hertz. Yeah? If our clock pulse is 1 hertz, that means for one complete period, low and then high and then low again, that is total time of 1 second, right? So if our time is 1 hertz, right, that would mean we need to hold that in the case of 60 for 60 seconds. We need to have a counter up till 60. But building a counter is very difficult. Building a counter to 60 requires how many flip-flops? We calculated this in our last class. How many did we do? We said it will take 6 flip-flops, yeah? 6 bits, 6 flip-flops. So our truth table will be 2 to the power of 6. 2 to the power of 4 is 16, 2 to the power of 5 is 32, 2 to the power of 16 is 64. 64 line truth table. Very hard, very hard. All right? Not hard, but very cumbersome. The concept itself is very easy, but you know, it's very tedious to do that such a long task. Now, what we do is, we could change our clock pulse. Remember, all our flip-flops are tied together. All our flip-flops have a common clock. Yeah? All our flip-flops have a common clock. Fair enough. Now, how about we consider that our clock pulse, instead of being 1 hertz, meaning period of 1 second, how about if it has a period of 10 seconds? How about if our clock pulse has a period of 10 seconds? How many hertz is that? That's 0.1 hertz. Yeah? 0.1 hertz. So how many clock pulses will it take to hold red for 60 seconds? How many clock pulses then? Only 6 clock pulses. Now, how about building a timer till the number 6, a clock counter till the number 6? Is that easy? Yes, it is easy. All right, so let's do that. Let's go ahead. So, In the first solution, I was talking about, hey, let's do count till 60, build a counter from count to 60. That's 6 flip-flops, 6 bits, 6 flip-flops. Too hard, right? Now, becomes too complicated, too complicated. So what do? We do something like what we did in the lab. Too complicated. 6 bits, 6 flip-flops, 64 lines on your state table. How about changing the T clock, the period of the clock, to 10 seconds, right? Therefore, to hold at red, which was 60 seconds, requires 6 pulses, 6 clock triggers, right? All right, so let's do the table now. So what do we want to build? What are we building? We are doing part of the project right now. We haven't built the final project. We are building part of the project. We are building the timer which will evolve, all right? Okay. So our new frequency for the clock frequency is equal to 0.1 hertz, which means T clock, period clock, not T clock. The period for the clock is 10 seconds. Yeah? Is it all making sense? So we have to count to 6. So let's look at the state diagram. It will be 0, 1, 2, 3, 4, 5. Yeah, that's already 6 back here. And obviously the number 6 should just point to 0. You see what I'm doing now? I mean, you guys are doing a much more difficult project. Your project is much more harder. This will be easier. Now, what is the output over here? Remember, what is the output? There's no input into the system. What is the output? The output is, we have output 0, 0, 0, 0, 0, and once it's, so 1, 2, 3, 4, 5, 6, then we get an output of 1. You see where we're going with this? And obviously, this will be output of 0. Now let's draw the excitation table for this. So we have our current state. Now, the number 6 is how many flip-flops? How many bits? 3 bits. Which means 3 flip-flops. Yeah? All right, so now we have current state, our next state, and our system output, our flip-flop inputs, Q3, Q2, Q2, Q1, Q0, Q2 star, Q1 star, Q0 star. System output is, let's call it Y. Flip-flop, let's use T. Okay, let's use T. What did the question say? What were we supposed to use? Yeah, okay. So we're using, let's say, T2, T1, T0. All right, let's just populate this side here. That's just standard population on the left hand side. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right. Now, 0, 0, 0 is the number 0. 0 points to, the next clock pulse will refer it to 1, right? 0, 0, 1. And the Y will be, output will be 0, right? In fact, to be honest, the way we draw this is, what type of machine is this? Is this a milli machine or a Moore machine? It's only the states of your thing which is determining the output. So is this the milli machine or Moore machine? Over here, what I've done is, I've done a reduced form just to make it easy to look at, right? Reduced form of your state diagram because there wasn't enough space. But if you draw a big one, what type of state diagram will you be drawing? Okay, the type of state diagram, this is not the answer, but the type of state diagram will be a Moore state diagram. Okay, a Moore state diagram, and you won't have any of this. There will be no numbers along the lines. All right, it will be just your states of your flip-flop and what your current output is. All right, okay, because that's your current output based on thing. Your current input, your current flip-flops is your giving your output. Okay, 0, 0, 1 will become 0, 1, 0, and your output will be what? Have a look at the state diagram. 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0. Now we have to see 1, 1, 0, 0, 1, 1, 1, and we have a 1. Is this correct? Does it match up with our thing? And over here we just go back to 0 and that'll be a 0. Right? So if you look at the count, we have 1, 2, 3, okay, 0, 1, 1, 2, 3, 4, 5, 6, yeah, and it should go up. After 6, flags up. All right, now let's do our table. Can you look at your table and let's fill this up very quickly. T2, T1, T0. Let's look at your table and fill that up. T2, T1, T0. Does this table match our state diagram? Let's just have a quick look. Got a feeling it's, so from 5 to 6. Yeah, sorry. This place here, that becomes a 1, that's a 0, right? Okay, yeah. Yeah. All right, let's fill the state table up. So after 60 seconds, if our clock pulse is kept at a period of 10 seconds, after 60 seconds, the output will become 1. The moment the output becomes 1, what happens? This feeds into another state diagram now. Can you see? This circuit is only a timing circuit. What are we building? We're building a timing circuit. All right, so we'll quickly fill this so that we can build that timing circuit. Okay, let's do this. Let's fill out T2. Anybody got T2 done? Yeah, that's a 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1. Oh, sorry, wait, hang on. 0, that's a 1, 0, that's a 1, 0, 1. Last one, that's a 1, 1, 1, 1, 1, 1, 1, 1. All right. So in the end, we get 3 flip-flops. And we tie all the clocks together. And then there's a T. This is T2, T1, T0. Now, oh, we've skipped one stage. Sorry, guys. We have to do the Carnot maps. Right, can we do the Carnot maps quickly? I can say clearly that T0, we already know. T0 is equal to 1. So you just place a 1 there. All right, T0 is equal to 1. Right? Can we do the 2 Carnot maps? I give you 2 minutes time to do a Carnot map for T2. Those guys on this side do a Carnot map for T2. Those guys on that side do a Carnot map for T1. All right? Okay. And then in the end, I just want your equations. Simple Carnot map, there's only 8 variables. 2 by 4. I've done Y for you. Okay? Okay, so T0 is equal to 1. You don't need to do a Carnot map. You just see the whole answer, whole column for T0, unless I made a mistake, the whole column for T0 is equal to 1. And Y I've done for you. Remember, you've also got to do Y. All right. Now, oh, I think there's another mistake here, guys. Did 6 go to 7 or did 6 go to 0? Yeah, just check that, eh? 6, I think, had to go to 0 according to our state diagram. So correct that. Okay, now let me show you what the general concept. All right, can you tell me what our T1 and T2 is equal to? T1, guys, who is doing T1? T1, this is the equation for T1. What do we have? T1, who's doing T1? This side. You guys doing T1 or T2? This side here is doing T1 or T2? T2. All right, tell me T2. So just call it out loudly. Yeah, what do you get? Q1, Q1, Q bar. Q1, Q0. Q1, Q0. Is that it? Just please take note that I think according to our state diagram, after this number, this fellow was supposed to go to 6. There's no number 7, eh? All right? But so long as this guy is staying 0, that's the main thing. Because it's our output which is important. Now, T1. What do you guys get for T1? Anyone? Just Q0. All right. Do you remember we did the lab on this? We did a lab on this, the last lab. Okay. Now, eventually you have some circuitry here. So I'm not going to draw it, but you have some circuitry. So let's just draw the Y, because the Y is important for me, all right? This here comes out to be Y. So it's Q2, Q1 bar, Q0. Q0, Q2, Q1 bar. Q1 bar is from here. And Q2 is from here. And that's your Y. All right. Now, of course, there's some other circuitry. This is incomplete circuit. And just take note of this guy here, eh? There's a problem there. There's a problem there, eh? All right. Now, what I wanted to say, guy, is this, that this circuit, you're feeding it the clock, right? Remember, what is the period of the clock? The period of the clock is 10 seconds. After 6 clock pulses, Y will become 1. Y will become 1 after 6 clock pulses, right? Something along those lines. All right. Now, after 6 clock pulses, Y becomes 1. Then, let's go back to our original diagram. The moment Y becomes 1, red becomes green, right? Red becomes green. You see what's happening here, right? Then after another 6 clock pulses, green becomes orange. So you have to draw another set of particular thing over here. Let's now draw the counterpart for this. This is another. This one here, we were just building, in this case here, we were only building what? Our timer. Our timer. What are we doing here? Let's have a look at that. So let us say, for this, maybe I'll draw it over here on the side. So the way to do it is, let's say the red is LED number 0. So that's LED 0, LED 1, LED 2, right? Okay. Set? Everyone happy? No, let me name it something else. Something, because 0, 1, 2 is very similar. Right, maybe a LED A, B, C. All right, now, The way we'll do it is, and let's say the order is A, B, C. If the order is A, B, C, what we will do is we have your A, so red is lighting up here, yeah? Red is lighting up. So if it's ABC 1, 0, 0, going to, maybe I use different color, eh? Going to, wanted green. Green is what? 0, 0, 1, yeah? Look at this, 0, 0, 1, LED C, right? Then we have orange, which is 0, 1, 0. And of course, you have your 0 hanging on, 0. Oh, I forgot, eh? Maybe, yeah, we'll put a, yeah, you put that thing there. A line, because this is a more diagram. And the moment you have 1, 0, 0, you hold it there for so many seconds. Right, but I'll just draw it like this so that we can see the thing. All right, okay. There we go. Now, this is our master. This is our master diagram. The thing what we were doing, trying to solve just then was how to hold it there. So there's another set of flip-flops called the counter circuit or the timer circuit, which is holding it there at red. Right? So 0, so the moment it becomes 1, then the number changes to 1. All right? Okay, then the number changes to 1. And that, the output from that circuit feeds into this circuit. Obviously, there are some other states, so we've got to take care of other things. So this is a basic circuit of how we can draw our traffic light system. All right? Okay, this gives you an idea. So most of the time, real circuits will have one flip-flop circuit sitting on top of another flip-flop circuit. One flip-flop circuit is handling the timing. Another flip-flop circuit is actually handling the transition of the lights. Yeah? Can you see over here there was only 3 transitions. And the timer circuit there were so many transitions. Alright? Okay? But we had to measure the timing here. We want it to be 60 seconds. But then there is another problem. We have to build a separate circuit for the timing for orange. Yeah? A separate circuit for the timing for orange. So what do we do there? We have to say if-else kind of statement. Right? If-else, how do we do if-else? Use the OR gate and AND gate. Alright? AND OR circuit to basically determine whether it's on red or green. If it's on orange, you have to flip on, enable another timing circuit for the orange light. So in the end, you'll have 3 sets of circuit. One circuit to time for 60 seconds. Another circuit to time for 10 seconds. Another circuit to the main circuit. And the 4th circuit is to determine whether it's on red or green. Right? Because, or if it's on orange now. If it's on orange, it's that particular AND OR circuit has got to choose or enable the 10-second timer. The 10-second timer, single clock pulse. Right? Okay? Any questions, guys? Have you got an idea now how it's sort of visualizing now? Right? Have a go to YouTube. A lot of overseas students in this course, I gave you a ring counter. In the other courses, they give their traffic lights as a project. That was one possible option. But I think the technicians were not happy with the amount of LEDs getting burnt, so they said, you give software project. Right? I think half the LEDs got burnt this semester. Right? I don't know, in 212 maybe. Okay. All right. So this is a real life project. We'll discuss some more projects later on. So the next lecture we'll talk about a stopwatch. How we can build a stopwatch. All right? Okay. So these are lots of real life projects which we will do. Okay. That's it for today's lecture. Slightly shorter than usual. We'll continue on Wednesday. All right? But we are now doing practical problems. Right? Which you should be aware of. Now we're doing the real deal engineering. Up till last week we were doing the building blocks. Now we are doing the real application problems. They call it real application problems. Okay, thank you.